Working?
No, I'm fine. So, thank you very much for the invitation to speak today. My apologies to Albert. He actually invited me, I think, 18 months ago to come and speak. And I think at that stage I wasn't even working at the University of Birmingham. I was about to start. But now I've made it, and I'm very glad to be here. There's only twice I've been to the University of Birmingham before, Exeter. First was a conference when I was a PhD student. I won't tell you when that was. And the second time was for my daughter's graduation, which was a bit more recent. My daughter graduated in psychology. Interestingly, after that, she worked in the research, whatever you call it, research services department. And one question was in her interview was, how would you cope with a senior professor who was trying to make you do something that you shouldn't do in terms of a research project? I think the answer in her head was that she'd lived with one for long enough to know how to deal with it. But I think she gave a much better answer than that, because she did work here for 12 months. And now she works in an administrative role with the Devon Constabulary. So I'm glad to be here. As Albert said, I've worked in a number of different places. And in the latter part of my career, I worked much more in university leadership or administration, and at De Montfort University and Nottingham Trent University I was on the university executive team with a particular responsibility for research and knowledge exchange. But in the summer of 2021, having done that for 6 years or more, I decided, whilst I'd enjoyed it, I didn't want to carry on working at that pace, and I think it was also connected to lockdown and COVID. Running a university through lockdown was, in many ways, interesting, but it was very tiring with the continuing changes in what we could do. So I stepped back from that role that summer, and now I work in 2 different roles, not quite adding up to full time, which I quite enjoy, because I'm also taking the opportunity to travel more than I did before. Or at least when I go to a conference now, I stay for 2 or 3 weeks. I used to stay for 2 or 3 days. The luxury I now have is that I can stay for a bit longer. And the 2 roles that I have are, in some ways you may think, very different. But it's interesting to look at the similarities between the 2. So I work at the University of Birmingham in the School of Engineering for the equivalent of 2 days a week. And what I do in that time is work on my own research. So I'm moving back into doing research, because I didn't really do too much of it when I was in a senior role. But I also work with other people within the school in terms of developing careers for earlier career and mid-career researchers. Birmingham has a long reputation in the area of water engineering, and we're looking to develop that even further now. And I also get pulled into other things given what I've done. So last week there was a promotions committee, so I was pulled in for that. And later this week they're interviewing for a structures position, so I've been invited to get involved in that as well. So I'm happy to help out with those. But it's a varied role. I do a lot of work internationally, as was mentioned. I have worked in Delft in the past. In fact, I remember David coming over to see us doing some other interviews in Delft when I was there. And now I particularly work with colleagues in China. And this year I'm going to spend 2 months working in the Chinese Academy of Sciences in Beijing, in the Institute of Geographical Science and Natural Resources. Hot pot will come up in my presentation as well, but later on. The problem with working in Beijing is you can't get particularly good hot pot. You have to go to Chengdu or Chongqing if you really want to. So I'm doing that this year and then developing research with people there. The other role I have is that I work in a small consultancy based in Bristol of about 25 people. But interestingly, my main role there is not on the technical side of the delivery of projects. It's on the management of projects, but also the management of a company. So given my experience in academia of managing large teams, particularly of engineers and scientists, there are parallels to that within a company of very highly motivated, very technically strong people. and how to bring those people together to work in teams and how to manage those people. So that's what I do with them. I mainly have been involved in bringing on board a new leadership from within the company and expanding the work that the company does. And I enjoy that combination, and I particularly enjoy the intersection between the two, particularly, as I say, in terms of leadership, but also feeding back some of the challenges that we face in the modelling in the company back into research, and then vice versa, seeing how the research can be of use within the companies. So what I want to do today is some reflections on what I broadly call urban flood resilience, and then give you a little flavour of some projects I've been working in, some recently, some not so recently, but that I think give a perspective on what I'm talking about. I've done work in the past, as I say, I've not been to Exeter before, but I've worked with people here, particularly with David. We had the 2 phases of a project with Colin Thorne, who was in geography at Nottingham. So some of that is reflected in here as well. Can you all hear me properly at the back? At the moment I have a problem with not hearing anyone here, which means I can't always judge the volume, but as long as you can hear me, that's fine. So what are the challenges we face in flood risk management at the moment? And I've picked a few of these. Clearly, I'd say climate change, and move on from that fairly quickly. I don't think there's much discussion around that, but that makes predicting the future much more difficult than it was for us in the past. Another issue is land use change and economic development. So we have a lot of cities that are developing. Even in the UK, land use is changing. But when you look around the world at emerging and newly developed economies, you find a lot of large cities in coastal areas that are vulnerable to flooding. And in the past, the approach may have been the very traditional approach to flood risk management, which can no longer cope with all the challenges that these cities face. So there needs to be further development in terms of the input into flood risk management, but also a change in terms of the approach that's taken. We have the uncertainty, which goes back to the first point, which is more to do with climate change, but also as we look at more and more complex systems, the input parameters that we get have uncertainty in them, and the models that we use to predict things also have inherent uncertainties within them. We need to ensure value for money. In any country, there's a certain amount of money to be spent, and you want to maximise the benefit from that. And again, as we look at more complex problems, making that evaluation is much more difficult. And I look in the UK at the moment and the work we do within the company, a lot of which is increasingly focused on nature-based solutions to flooding, and our knowledge of how to predict the effectiveness of nature-based solutions is certainly not as well developed as our knowledge for working out the benefit of much more harder traditional defences. And we do some work within the company trying to address this, which I'll talk about later on. Anticipating my next bullet point. Stakeholder involvement. And I was talking to somebody earlier today about this. The involvement of stakeholders is important. First of all, to find out what the problems are in a particular place. By talking to people in the area that you're studying, you can find out about what actually happens in a flood. But also having that involvement means that when you are developing responses to the flood risk in that place, you are able to get feedback on what the people there actually want. And some of the work we did in the 2 projects that the second part David was involved in was developing groups in a particular area, and this work was done in Newcastle. So representatives of people that are farmers there, people that use the parks, particularly people who have dogs, because they walk around the parks 2 or 3 times every day. So if you talk to dog walkers, you learn a lot about what happens in that particular area. You talk to businesses in the area, you talk to the local authority, and try and bring those people together in a group to discuss flood risk in that area, so that we as consultants or researchers learn about the problem, but also we can talk to them about what approaches are possible, but not necessarily telling them what to do. So the community can gain some knowledge which allows them to propose what measures should be taken. And in some cases, that may not be something that is about completely stopping flooding in their area, because they may not want to build a lot of concrete walls. They can decide what balance they want between hard measures and the softer measures that can be put in place, and develop a response to the flooding that is suitable to them. It takes a bit more time, but from the point of view of the decision makers who are putting the money up, it means that the solution that is developed is one that has a wider acceptance within the community. And I do think we have so many models now. Within the company, we use one in particular. We do have a license for another one, but we don't use that one so often. And everybody's pushing a particular model because they all have slightly different bits that they are very good at and other bits they're not so good at. But it can get very confusing for people procuring advice on flood risk management, that there are so many of these. I don't have an answer to that problem, but I do think it becomes an issue, particularly in the commercial, for the people who are procuring this advice. Opportunities. Interesting, in the past couple of decades, the big change has been remote sensing. That's had an impact in terms of us knowing the terrain height. So we know where the land is and work out how the water moves over it. What we haven't got as a significant a development in is the inflow into the problem, or the rainfall. That real-time sensing of how much rainfall is going into the system, or what the water level is. And there have been a number of projects about developing cheap remote sensors that we can just put in. They cost a few pence. You put them into an area, and they'll give you real-time data on river levels and rainfall. They're not yet at a state where we can use them throughout the system. So I think we still have an issue to get the same improvement in terms of real-time measurements that we've had from the remote sensing that we've now got. The remote sensing has moved on tremendously. We can now get data for most of the globe, and people are building flood models at that scale. So it is not, there's still more to be done there. The next one is the compute power that we increasingly have available. Allows us to run more complex models. I think we have to think very carefully before we immediately go to the more complex model. And I'll give an example later where a simpler model is actually more justifiable and of greater use to the end user. So we always have to bear that in mind. In my own company, we have that tension. We have a fairly complex model that we use, but some of the requests we get from clients, the answer is really, you don't need us, you need somebody else to do it much cheaper. Now, machine learning, this is always quoted. One thing that surprised me since I've moved to work at Birmingham is how many applications I get to do PhDs. Far more than when I was at Leeds. I don't think it's because I'm a better supervisor or a more popular person than I was when I was at Leeds. I just think it's advertising and it's social media. And everybody who contacts me about doing a PhD wants to use machine learning to solve flood risk problems. So I've become more and more cynical about it. I do think there's potential. If somebody emails saying they want to do a PhD in machine learning, I have to take a deep breath and then start to talk to them. And what I decided to do was to look back for some early work that was maybe done in terms of what we could call machine learning. And this is the project that I found, and I think you will recognise the name there. It was 1997. So Professor Savage was doing work with neural networks in 1997. And I think in 98 I went to the Hydroinformatics conference in Copenhagen, and Dragan was there and was probably presenting similar work to that. So we have been looking at machine learning methods for a long time. But now I think we obviously have much more sophisticated algorithms for the machine learning. There's been a lot of development of that. And also we have much more compute power. I think what we don't have so much in flooding compared with what's done with things like ChatGPT. ChatGPT has a huge database of language to learn from. And people talk about big data in flood risk. And in terms of big data, we do not have big data. For me, the definition of big data is data that we cannot at the moment analyse because we don't have the tools to do it. I think the tools we have in flood risk management are adequate for the amount of data we have at the moment, and are probably adequate for more data than we have at the moment. So there is potential there, but I think it needs something of a sense check. Urban flood resilience is something the group here has been very much involved in, and when I worked in Delft, we established the flood resilience group at IHE Delft, as it's now called, headed by Chris Savenbergen. And what I'm going to talk about now is a bit on flood resilience and some reflections on it, very much based on the work that Chris has done over the years. So that group was established in Delft. I checked in 2005. So it's been worked on for a couple of decades now. This is a very good overview if you want a primer in terms of flood resilience. Read the paper by Chris Savenberger and his colleagues to get that. And this is, many of you will have seen these sort of ideas before. In the traditional approach, there's assumption that the changes in the system are predictable. We can actually control it. And from the governance perspective, you can have that sequential planning process. I was actually reminded of the second key objective when I was having my hair cut the other week, because it was in a place that where there'd been some flooding the week before, and it was the flooding of a football pitch, which from my point of view is a great example of resilience. If your football pitch is flooded for 5 days of the year, it's a very effective flood storage system. And okay, for 5 days of the year you can't play football. It's not a Premiership football team, they're not going to lose money. So it's a good response. But the person cutting my hair said, it's a shame they can't prevent it. And I thought, I'm just trying to get my hair cut. Well, actually, I'm a professor of flood risk management. It didn't seem to be the best answer. But there is still a perception in some parts of society that we can control it. And that is that old paradigm. Whereas when we move to the flood resilient approach, we accept that the future is uncertain. We have to build the adaptivity into the responses that we put in place. So if things change in 20 or 30 years, we don't have to throw everything away and start again. We can change. And I know work has been done on that in Exeter, and the group in Delft were also working on that. So in terms of the governance, this means it isn't just from the decision maker's point of view, they can look at the problem, decide to spend some money, and then think that problem's solved, and they can go and move on to another problem in a completely different area. It does mean there has to be continual evaluation of how the system is working and changes that need to be made to it. And there's still a tendency in that in the UK. Last week there's a lot of discussion in the press about investment in flood risk management. There's been very little of that for another year or two, and then it will come back again. There isn't that continuing focus. So in terms of the work that Chris and colleagues have done, they talk about these different stages to the approach to resilience: engineering resilience, ecological, and then developing further into social ecological resilience. And the engineering is much closer to the previous approach that we took of flood defence. It then developed further into looking at the wider environmental context for some of those measures. But now, as Chris argues in the paper, it's much broader. It involves the societal system, which does have an influence on what sort of response you might want to put in place. So the engineering, the natural science, and the societal analysis are all now integrally linked. One of the great things for me when I worked at IHE in Delft is that Mike Abbott, who was retired by then, used to turn up once a month. And he was just seen as part of the furniture. Anybody knew him. So for me to walk into the coffee room and Mike was sat there on his own with a cup of coffee, that was the next hour and a half gone. But it's an hour and a half that I always found challenging, but also very productive. He always talked about hydroinformatics being a socio-technical system. And he would often talk in quite vague terms that made it difficult to understand. But over the years, I remember those conversations in this context, that we have all slowly moved much more to do that. And in the paper, Chris and colleagues conceptualised this as on the left is which was the previous way. There's an event, so you go down the curve to the bottom and then recover from it. The ecological one would have that happening again and again, but now they're arguing that the paradigm is very much one where you have an uncertain future and you'll move to different positions and then you'll change where you're going to go later on within the system. And they outline 5 features which I think follow quite nicely from one to the next. So what we know can never be perfect. As scientists and engineers, that's probably the most difficult thing to accept, that we don't know exactly what's going to happen or exactly how the system is behaving. So the things will happen in the future that we did not expect. There's a parallel back there to managing a university or a small business. Stuff happens. You can't always predict what's going to happen. So you need to be adaptable and not be thrown when something happens that you weren't expecting. So it means you need to take that long-term view, but you have to develop the capacity to monitor the systems and look at how you can make changes along the way. So that means looking at the whole range of potential interventions to reduce flood risk. And that's the other thing you have in conversations with people who don't work in the area of flood risk. Everybody says, why don't we do this? Why don't we stop building in the floodplain? Why don't we build more defences? Why don't we do this, this or this? In a way, we need to do all those things. We need to look very carefully before we build in floodplains. We do need to build defences. We need to protect properties at property level. We need to make sure people can get insurance, because that is a form of flood resilience. Your house is flooded, which is not good, but at least you have the financial ability to restore that house. For people who aren't insured, it can be very difficult. And one of my students at the moment is looking at the impact of flooding on small businesses, which is, in total, is a huge part of the British economy and most economies. He's from Malaysia, and he's looking at it from that perspective as well. And for a small business, if their property is flooded, that could well be the end of the business. If you're Sainsbury's supermarkets and 1 or 2 of your shops flood, it's unfortunate, but the business will carry on. But if you're one shop or one hairdresser's on their own, then that can be the end of the business. And I think in all countries we see these small businesses. And that comes on to the point I was making, that there's a need to facilitate this participation and have this collective action and learning to bring people with us to gain some knowledge so they can make decisions about what they want to do in their particular situation. So what I'm going to do now is run through a few different projects briefly. If you're interested in any of them, I can point you to more details for these. And some of these, as I say, were done in the projects a while ago, and some are more recent. What we wanted to look in the last part of the Blue Green project, and the one that David was involved in, is how the measures we take for flood risk can either be to the detriment of previous systems, other systems, or to the benefit of other systems. Because we always argue that we have to look at the integrated urban system. But I think when we're working on flood risk, we see it as integrated, and it's a hub and spoke. And the hub is flood risk management, and the spoke are all the other areas. But if you're a transport engineer, the hub is transport, and everything else is a spoke. Now, it's easy to say, because if we then look at it as a system where nothing is at the centre of it, it becomes particularly complex. But we do need to look at the impact that flood risk has on other parts of the system. So we invented this rather cumbersome word, interoperability, to look at how the different systems might impact on each other. And we gave it this definition. And then we want to look at how we can actually actively manage some of those connections. So this is looking at, it's got a mind of its own. Stopped. Good. Look, this is an area of Newcastle. There's quite a green area. You can probably just see it. Just above that black circle, you can see it's all got a consistent colour. That's a green area, a park, which people locally value very much. So we can look at different parts of this area and try and see where there is the greatest scope for implementing blue-green features or sustainable features. So an area like that might have a high flood risk, but there's a low population density. There's a road there that isn't critical to the transport system, i.e. if it is flooded, it's not as if the whole city is going to be jammed up, and it's close to green space. So that's one where we might be able to implement some measures, retain some water without too much trouble. So we identify these different hotspots where there is this connection between recreational transport and the flood risk system to see what we can do there. And then we do some analysis of this area, and this was done with, thank you very much, Alice. This was done with
orange.
The orange one, thank you. This was done with colleagues at the University of Newcastle using their CityCap model. So what we look at is that representation of that previous diagram showing us the different features that we could work with. And then we look at if there's a flood, how many points in each of these squares is there going to be water greater than 1 metre depth. We choose that analysis. We can look at volumes, we can look at areas. But for this, to demonstrate the concept, we just looked at the number of points in there that was flooded to 1 metre. And then, so we take that prediction of what the where's the greatest area for the impact. This one's the area as well, and we do a classification from the map of what there is in terms of the infrastructure. So the green here is the roads, these blue areas are the park areas, and from this we can work out what action we could take in those particular areas. And having worked out where is the greatest, what area has the greatest influence on the flooding throughout the system, we can start to map these two together. So where should we be making interventions based on the flood risk prediction, and what interventions could we make in that area? So we then come up with 3 maps saying, well, these are the areas where it's very useful to retain the water, this is where we relieve the impact of the water locally, and this is where we actually resist it. So we might build harder measures in this particular area. So it gives us some insight in terms of making decisions as to what to do where and when. Now, so we worked on this in Newcastle, and we did some work on it in Leeds, because the PhD student working on it was at the University of Leeds. And in doing that work, we engaged with Yorkshire Water. Took us a little while to get the data out of them, as usual with water companies. But in the end, they were very interested in the research because they wanted to work out where to invest their money to get the maximum benefit. But they use something called a capacity assessment framework, which some of you may be familiar with, because I understand from Yorkshire Water that it's used there. They find it relatively easy to use, and also it's Yorkshire Water claim is fairly standard. So we applied this to the city of Leeds. Leeds is a large city, it's about 750,000 people. For comparison, it covers 8 parliamentary constituencies, so it's a large area. But it also has one local authority governing it, which means that there's one local authority responsible for surface water flooding throughout this area. Different catchments, mainly coming from the west or the northwest. Not huge rivers, but of a reasonable size, and they do cause flooding in the region. And there do seem to be a flood alleviation scheme. So we use this methodology that Yorkshire Water uses. They break it up into hexagons. In each hexagon you colour it according to a percentage of the pipe network in that hexagon that has that is going to be at capacity in a particular range of events. And so with them we work to predict what would happen over the next few decades based on particular climate. And the idea is we then will feed this into the previous analysis to look at where it's most effective. This gives some of the numbers that back up that diagram. And then this one takes us away from that percentage to a risk level and some involvement of the areas where we could take the retain, etc., measures to develop that, to reduce the flood risk. So they're now looking at how they can use this to make their particular decisions. The next project is actually one from the company, and this is based on looking at nature-based solutions. So there's quite a bit of work being done on that. Upstream of Leeds, along the River Aire, there is a town called Hebden Bridge, which regularly floods. I'm never sure the right way of describing it. It's a town that a lot of university staff live in the town. It's a centre for artists. It's a very alternative sort of town. So they don't want any flood defences there. They don't want concrete. You mentioned concrete, that's the end of the discussion. What they want is nature-based solutions. To me, it's almost an aesthetic judgment. I don't reject nature-based solutions, but sometimes it's almost driven by aesthetics rather than practicality. So a lot of the nature-based work has been done in places like that. There's a strong local community advocating an approach. There's a big upstream area of agricultural land. In Hebden Bridge, a lot of it is owned by large landlords who use it to hunt for birds, for grouse. And they make a lot of money out of selling licences to do grouse hunting. So you can imagine the town of Hebden Bridge and these landowners don't mix in the same social circle. If you get them together, you tend not to get too much agreement. So Hebden Bridge is a particular place for that. The other place where a lot of work was done was Pickering in North Yorkshire, which is a very relatively small town, a bit larger than a village. And I'd always said it would be good to see how this could be applied in an urban area, but it's much more challenging in terms of the constraints due to the infrastructure. So a project we took on within the company was working with the borough of Enfield, which is one of the boroughs in Greater London. And part of this feasibility study for the development of the Thames Estuary into the latter part of this century said that there was a large scope for nature-based flood management within that catchment. So Enfield were very interested in developing this. So we worked with them on a project to allow them to make the case as to how the nature-based solution would work. So we had proposed measures, and from that we assessed the damages, which is, I think, the novel part of this in terms of the consultancy project, and made an economic appraisal. There's also some novelty in how we represented the nature-based features themselves. And as I say, I can give you more details on this. I'm just going to run through it very quickly. In a lot of work on nature-based solutions, where you've got an upstream area where you're trying to retain water to reduce the flooding in the downstream urban area, the upstream area is represented by one parameter. There's a hydrological model that says the inflow into the system is going to be this much. What we wanted to do here was to reflect the heterogeneity of that upstream area. Because Enfield are fortunate in some ways. They have golf courses in the upstream area, but the council owns the golf course, which is perhaps the main reason it works here, because the council can change the way the golf course is managed. And they have other... Sorry, somebody doesn't put the microphone on. Is that me coming back? Is that better? Yeah, that's fine. Thank you. So they've got that benefit because they own the land and they can manage it. But it means they're doing different things. They're putting small check dams in the corner of fields. They're reintroducing trees in certain areas. They're creating more open green space with grass to retain water as source. So they wanted to represent all of these features within the model. rather than having a lump model across the full area. So we were interested, and we took on the project with them to do that. I think in the end we didn't. We would have made a loss on the project, but of course we're going to try and sell the work to somebody else now, which is the nature of consultancy. So this shows you the area. This is where this is the urban area where people are living, and then we have the upstream area, which we want to represent with a full direct rainfall model onto those particular features. So you can probably see this green line. That's the edge of the area that we want to model. But what we do have is we actually build not two separate models because they run simultaneously, but we look at this area down here, the urban area in this case, and then this is where we're going to be implementing the blue-green features. So we actually connect them along a line just here, because that's where the main flow is from that upstream area to the downstream. And this goes a little bit into modelling. This is where that interface takes place, so water running off from upstream comes across here. You can see with this grid, we're not getting a particularly good representation of the DTM at that interface. So what we developed here was this grid that's adapted into that interface to make sure we capture it, but we don't use that size of grid throughout the whole borough of Enfield, because then the model wouldn't have been feasible. This is the sort of thing they're looking to implement. They've started some of it already. And this shows us, this is what the hydrograph would have looked like downstream. Originally the light blue, with different variations of the model that you put in, you get a significant reduction in the peak. Obviously here, the hydrograph is higher here, but we've effectively squashed this hydrograph down to the lower one. So all the water drains out in the end, but there's a much lower peak. And then we've done work from that, doing the cost analysis and producing the economic appraisal, which Enfield have used to justify taking this approach rather than a more hard engineering approach. When you work, moving on to another project, when you work with the more sustainable features, a big issue that comes up is sediment transport. For a number of reasons, it can cause damage. I always said, if your house is flooded with clear water, it's not good. But usually your house is flooded with water that's full of sediment. And you look at a lot of rivers in the UK, by the time they get to a city, the rivers are brown because they're full of sediment. This is an extreme example of it, an area where some very nice cars have been fairly seriously damaged because of the sediment that comes down with the flood. So looking at the sediment in the flood event is important. There's another issue with flooding if you're looking at sustainable features. And this is that if you're putting ponds in to retain water, there's a concern that the ponds will fill up with sediment, and after 10 years they may no longer be able to retain the water that they're supposed to. So we did some work, again in Newcastle, looking at the sedimentations that you get in these areas. So first of all, we demonstrated that the flooding in the main channel, so the main channel is here, the flooding in the main channel is reduced when you build one of these ponds. The water is retained in the pond, but you do get some sedimentation. But what we did here is rather than run we ran the particular events, the 30 and the 100 year, but we also did some long-term simulations. So as well as the 100-year event, we ran a 50-year simulation with a hydrograph, constructed hydrograph going through that, and calculated the amount of sedimentation in the ponds to show that implementing this measure would not lead to a significant maintenance issue. And it's the maintenance that really bothers the developers. So the developers, if they're going to put up houses, they want to build the houses, they want to leave the development, and they don't want to have to go back to it. Somebody has to be responsible for maintenance. So we're trying to show that that maintenance issue was not as significant as they might fear. The next one is with a former PhD student of mine, Guan Fu, who now works at the University of Hong Kong. It's some work that we did in the city of Chengdu, which is the connection back to hot pot. Because Chengdu is the best place in China to eat hot pot. If you're from Chongqing, you don't disagree with me, I'll see you after. See there was this significant event. And this work done by one of Fu's PhD students looked at a number of different aspects. I want to particularly focus on the question of what scale of model to use to answer the question that the decision makers have. There's some other work in this which I'll mention, and you can find out more in the paper that we've published. So it's very much urban. There's an urban model. The drainage model's in there as well. The surface water model is connected to that. There's not a lot of data. So there's an issue of collecting the data to define the model, but particularly an issue around the data to validate the model. And so one thing they did to try and validate the model is collect crowdsourced data, because obviously with these sort of images on social media, this would be pictures from people sending in on WeChat. You get a geotag for these pictures, and then the student's done some work looking at the pictures and trying to also look at the Google Maps type data to check that the position that the photograph is meant to be from ties in with what you can see in Google Maps and other sources. And there's reasonably good agreement. The benefit of crowdsourced data is you get a lot of it. The benefit of gauge station data is it's very accurate. So this data is not always accurate, but you can get a lot of it, and there's obviously a trade-off between the two. But what we wanted to do here was to do a model at a very fine scale, medium scale, and a much coarser scale. So we did the fine scale model first of all, and then we interpolated the data up to a coarser scale, and therefore ran simpler and simpler models till we came to that one there. We used the same model, but obviously the results aren't as good because the grid is much coarser. The next thing I'd like to do is actually run different models for these, and run models that are suited to that level of data. But the purpose of this work was for the local authority to be able to react in an emergency situation. So they're really looking at sending emergency response teams to different parts of the city. And if they've got a 4-hour or 8-hour notice of where to send the teams, that's very useful. It's a big city, 16, 17 million people. You can't move around it. You can't be at the other side of the city in 5 minutes, certainly. So you need some warning for them to plan how to respond to it. And what we find working with them, talking to them, is that this information is much more useful because it's giving them the information at a district scale within the cities. And these are the districts that they use to run their local operations. These are the governance districts within the city. So the reason I wanted to show this was this point that also when you do the coarser model, sorry, you can't see that, so you take my word for it, there's much less difference between these two, because one of these has got greater amount of representation of the urban drainage. So the decision makers have much greater confidence when they're using the coarser model. It's okay, thanks. When they're using the coarser model than when they're using the much finer scale model. And they find it much easier to make the decisions they make. So that's a point I've always made in the research I've done, that you really need to decide at what scale you need to model. And the ultimate thing is, what is the question you're trying to answer? Of course, even myself as a researcher and in the company, we always like to show how great the model is at coming up with really big solutions. How big a grid can you get into your model? Several millions. Are we going up to 10, 20, 30 million cells? But sometimes that isn't necessary in terms of making decisions. Yeah, thank you. Thanks very much. Very happy to say that.
Thank you very much, Nigel. Any questions? Hello, Nigel. Thank you for coming.
what is the benefit of aggregating results about pipes on a hexagonal grid rather than on regular quadratic grid?
I have to be honest, I don't know the answer to that question. I know that's what Yorkshire Water do. Yeah, if it was squares, it wouldn't make a huge difference. I mean, you've got to have something that tessellates, but squares tessellate, so do hexagons. I will ask. And if I get an answer, I'll let you know.
There is some routing analysis done with hexagons. I think it's Uber have a hexagon-based cartographic system, for routing planning. So there are other advantages of hexagons, and that is being used more and more for analysis.
Yeah, right.
Be elements of the association of the adjacent risks as well, if you want to.
You see, I think also I did some work. One of my earlier papers I published with other people was using triangular meshes for flood inundation. And we thought it was great. And at the time it was great because you could refine the triangles down into certain areas. So in the river channel you had very small triangles and then you had bigger ones going out. But then everybody started to use remotely sensed data, which arrives on a Cartesian grid. So we all switched to using squares because that's what the data is like. But they haven't got data on a Cartesian grid, it's pipes. So they don't have to use squares. So it may be something like that.
You mentioned one of the opportunities is remote sensing. Now, does this make prediction or modeling less favorable in some occasions?
I think the point is the remote sensing for terrain models has made a huge difference in the last 20, 30 years. That's been great. But if I'd like to know what the water level is every 10 metres along the river, and we actually don't have that. At the moment, gauging stations on rivers are several kilometres apart, so it's difficult to make predictions. And I live, my house is in the 1,000-year floodplain, but there's a very extensive defence system, so I'm at a very low risk. But, so where I live, as you know from when I was getting my hair cut, there's always flooding. So the last 2 weeks has been flooding. But people say to me, it's always in a different place. And it is, but it's the river's pretty big. It probably got up to about 700-800 cubic metres per second recently. The flooding always pops up somewhere different. So having the level of gauging in the river that meant we could see how it was rising and going down in different places, as tributaries come in, as there's drainage in from the urban areas. That level of pervasive, remotely sensed data of river height or height in channels would completely revolutionise what we're doing. And I'm not going to name the university, but it was a long while ago, the university had this grant funding to build a sensor that you could just put into the banks of rivers and it would tell you where the river level was. So you've got to combine the sensor with the wireless to transmit the data back. And then they did it, but it's the size of a brick. So it worked, but it was too big. And I've still not seen anybody just design one chip that we could put in the riverbank and use it to get that data. So that's what I mean when it's there's a great opportunity if we can do that.
David?
Thank you very much, Nigel, for the talk. I'm going to pull out a bit from my question. You've described, I think, implicitly at least, over your career, the kind of move from flood management to perhaps to flood risk management to perhaps flood resilience management, if we can call it that. What do you think has been the greatest advance over that period?
Because I've just answered that question, I might say remotely sensed data. I don't like to show how old I am, but when I was first working in the university and we had graduates, I would come sometimes visit them when they're working in the company. One had gone to work in an engineering consultancy doing flood risk management. They had a paper ordnance survey map, a ruler and a pencil. So they put the ruler across to get the cross-section line and they read the contour levels. Well, this contour is 40 It was metres, I can't remember. It was at 40 feet. 40 metres, this is 20 metres, and they read off from the ruler and they put it in a spreadsheet. And that spreadsheet is what drove the one-dimensional model. Whereas now we just get the LiDAR data in, you can do all sorts of things with it in GIS, and then you put it into the model. So that's been a huge change. But I think the bigger change, and this is one that really struck me when I was working in Delft, because in the institute there's so many different disciplines, but everybody's working on water. It's bringing those disciplines together, and the recognition that it's not just engineering, there's geography and natural sciences, there's the societal aspects of it, and law is a big part of it. So it's bringing it together in those different disciplines, which is challenging, but exciting and productive. So the fact we can do that is great. Hi.
Hi, thank you very much for your presentation. And I remember you mentioned in one of your projects you do the National Base Solutions Assessment in London, and you use just a direct rainfall model rather than the hydrodynamic model or hydrological model. How do you do that? I mean, realize that just to use a rainfall model.
Yeah, we have, I think in that case it was a 3-metre grid over that area. And we're actually putting the same amount of rainfall across the whole grid. So I think your question might lead to another question, which is what do we do if the rainfall varies?
Yeah.
But we've assumed uniform rainfall in that case. The next stage would be to look at a larger area with different rainfall. But we just put a certain number of millimetres of water that falls there. Some of it is infiltrated, and then some of it runs off, and it runs off according to the digital terrain model. Is that clear?
Yeah, you mean you just use the different rainfall on the different surface?
We put it onto a 3-metre grid of cells. So in that 3-metre grid, there's a certain amount of rainfall going in. Because before, we would have taken a whole area of several square kilometres and just said, that's the area, this is the rainfall. There's a factor that decides how much of it is retained, and then the rest of it goes into the model at that one point. But we actually now get the variation in the rainfall runoff over the whole area and how it goes into the downstream area.
Do you still need other model to
Yeah.
capture? Yeah.
That's
yes.
why, probably why nobody's tried to do it before, because there's so much compute time taken in the model of that upstream area. Whereas in the past you would calculate one number and put it into your downstream model. We spend a lot of time. And with that grid refinement, if we'd used that grid everywhere, we worked out that the full set of runs to do the cost appraisal would have taken 1,000 years. Whereas it took us 3 weeks, because we had a very large grid in most of the